Okay, if you're watching this on YouTube, front row, other slackers, I'm already annoyed with you. It's senior skip day. I'm a senior, believe me, I didn't skip, I'm here. Where are you guys? Yeah, we deserve it. No, you don't. And by the way, if you're gone and you're watching this, I have no sympathy for you whatsoever. I don't understand. Tough. Okay. No, I'm serious, like no sympathy for you whatsoever. I am so annoyed. All right. So let's talk about what happened here. Hopefully you didn't break physics, chemistry, whatever branch of science that you want to talk about.
I mean, we got pretty close.
So you got the CuSO4.5H2O, right? Now, with that one, did the temperature go up or did the temperature go down?
Went down.
With the hydrated?
Yeah,
right?
down.
Okay. So it probably went down a degree or two. Now, here's the bigger idea, okay? And especially if you compare that to the anhydrous, which is CuSO4. So with the anhydrous, hopefully you saw the temperature go up, okay? So this one, the temperature went down, and this is a nice contrast to show endothermic versus exothermic reaction, okay? So if you look at what happened in terms of like on an atomic level, we can't observe, and this is the whole idea of thermodynamics, and this is frustrating, is that you can't observe directly what is happening. You observe what's happening in the surroundings. And from that, you can infer what is happening with the system. Now,
he's being stupid.
If you be stupid, don't be loud and annoy me. Okay. So here, there are certain things you have to know without hesitation. One, the sign of delta H. Delta H versus positive versus delta H being negative. The other idea of what's going to happen when you break bonds versus what happens when you form bonds. So here's the deal. If you have a negative delta H, is that endothermic or exothermic?
Exothermic.
Exothermic. You should know that, no hesitation. Boom. Okay? Don't make a flashcard. Do something. Positive delta H is endothermic. If you break bonds, okay, like let's say for example, here's a water molecule. So if you break the bonds that hold that together, that requires an input of energy. Like I've got to grab these and separate these out. So breaking bonds is an input of energy. When you form bonds, if you imagine like this, and when I do that and you hear it, okay, that was a release of energy. So you release energy when you form bonds, you have an input of energy when you break bonds. So here's the contrast between the two of these. If you look at that CuSO4, so it was a copper, a sulfate, and around this you kind of have a satellite of water molecules. So here's what's important. The water molecules are already attached to the copper sulfate. That's what made it the hydrate, okay? Technically it's called copper 2 sulfate pentahydrate. Penta means 5, okay? And the hydrate means you have 5 water molecules. So the technical name of this is copper sulfate pentahydrate. So you put that in water and it dissolved. Okay, so anytime something dissolves in water, and the golden rule of things dissolving is that likes dissolve likes, okay? So if you see something dissolving in water, and we'll get more into this in the next unit on polar molecules. Water is a very polar molecule. The oxygen end is negatively charged and the hydrogen end is positively charged. So what happens is that when you put that copper sulfate in there, if you focus on the copper sulfate, copper is positively charged and sulfate is negatively charged. So the copper ion, okay, you let this be the copper ion, because that's positively charged, that's going to be attracted to the negative end of the water molecule. So this is a tug of war. If something dissolves, it's because the attraction to the water molecules is greater than the attraction to the ion that's there with it, okay? That's what allows it to dissolve. If the bonds that hold that together are stronger than the attraction to the water molecules, it won't dissolve. This is why you all don't dissolve when you wash your hands, okay? Your skin is slightly attracted to the water molecules, but conveniently the molecules that make up your skin are more strongly attracted to each other than they are to the water molecules. If that was not true, and the molecules that make up your skin were more strongly attracted to the water molecule, bad things would happen. It's like, did you wash your hands? Yes, I can tell because part of your skin is dissolved, okay? That would not be good. So, when this thing dissolves, the copper forms a bond with the water molecule. So, when you form that bond, that's going to release energy. So you have to have two inputs, two deals with energy here. You have to break the bonds that hold the copper to the sulfate. That requires an input of energy. Then you form a second bond with the water. And when you form that bond, that's a release of energy. So you have an input of energy to break bonds. You have a release of energy in the formation of bonds. Now, on that first one, the temperature dropped. So what that means is that the input of energy to break the copper sulfate apart was more than the energy that was released when the water bonded with the copper and the sulfate. That's why the temperature went down. Now, in sharp contrast to that, you have the anhydrous copper sulfate. So with this one, the temperature went up. Because what happened is that, number one, it required a certain input to break the copper sulfate. That's going to be the same on both of them. But what shifts the second one, that anhydrous, is that you're looking at that going, whoa, that copper sulfate still wants to form the pentahydrate. So you're also going to form a whole bunch of bonds with the water molecules. And the formation of all of those bonds to make that pentahydrate released energy, and that's why that temperature went up. Now, don't think about this too much. I'm going to tell you right now, how did the temperature go up? Oh, it's photons, okay? Water gained energy, the particles moved around more. How'd they move around more? There's a little gas pedal, you press down on them, they move faster. There you go, they got accelerated, okay? Just accept it. So, here's how you know that the particles gained energy. You saw the temperature go up. And if you remember that thermometers are radar guns for particles, that makes sense. It's like, oh, okay, right, the radar gun read a bigger number. Particles are moving faster. How'd it happen? Don't worry about it. You're just going to end up in the corner sucking your thumb doing drugs. Don't, okay? Just accept the fact that they're moving faster. Don't get hung up on the mechanism. It would just lead you to pain and despair and agony, okay? Just accept the fact that they're moving faster. Just go with it. So, now you get to the backside. Let's say that I gave you a crucible of hydrated copper sulfate, okay? And I said, hey, I want you to change that from hydrated copper sulfate to anhydrous copper sulfate. So what you would do is that you would put this underneath the Bunsen burner and you would heat it up. Now, why do you have to put energy into making this the anhydrous? Kevin.
You need energy to break the bonds between the water and the CuSO4.
Beautiful. You're going to break the bonds. This is the classic example. Oh, great, I'm going to break bonds. I have to put energy into the system, okay? And you're going to break those bonds, okay? Energy is going to go in. Then when you get done, now you have the anhydrous. If you take the anhydrous after you heat it up and you let it cool back down, and you put water back in with it, the system heats back up. Because then, once you put some drops of water back in there, then that is gaining energy because of the fact, or you're releasing energy because you're forming those bonds, because you're remaking the copper pentahydrate. So That's the beauty of this scenario. You're going, okay, cool, right, got it. Break bonds, energy goes in. Form bonds, you release energy. There's no exceptions to the rule, okay? And so when you see, so for example, all of you right now are little thermoses, okay? Your furnaces. Are you guys, is your overall body process endothermic or exothermic?
Exothermic.
How do you know?
Because we release body.
You're giving off energy, okay? All these little cellular factories are giving off energy, okay? You give off heat. If your entire cellular process was overall endothermic, what would happen?
We have to lay on the rock and sun ourselves.
Yeah, you would have to get warm because of the fact that instead of giving off energy to maintain your thermal processes, you would always have to be taking in thermal energy, which is not conducive to environmental stability. Let's just leave it at that. Okay, now, so here's the confusing part. But if you think this through, this makes sense. And this is all about switching the sign. So on that first part with the pentahydrate, your temperature went down. So you're going to do Q equals M delta T C sub P. And this change in temperature is going to be a negative number. Okay? This is going to be a negative number. But this is for the surroundings. We're after the system. But this hinges on the idea that energy lost equals energy gained. Okay? It's one of the laws of thermodynamics. Okay? First law of thermodynamics. Whatever energy you lose has to be gained somewhere. So when you calculate this, you're calculating the energy that was lost by the water. And you know it lost energy because the little speedometers decreased, okay? You slowed things down. So Q for the surroundings is a negative number, which means Q for the system is going to be a positive number. So this is why when you calculate that delta H, you're going to have a positive number. So you're going to take the Q value that you have. You're going to switch the sign. You're going to divide that by the moles of your hydrated copper sulfate. Boom, there's your enthalpy. Okay? Now, in contrast to that, you have the second part of the lab. When you took the anhydrous, you put it in the water, you dissolved it, the temperature went up. Oh, okay. So Q for the surroundings was a positive number on the second part of the lab, which means your delta H for the system is going to be a negative number. Okay? Does that make sense? This is why you have to watch the signs. Okay? You have to watch the signs, you have to watch the vocabulary. Hey, temperature goes up, temperature goes down. Okay. So hopefully that answered a lot of those questions. So let's talk about this last question, where you've got like these different bonds and things like that. So visualize this. So where I have chlorine somewhere, lost it. Okay. So let's say here's the chlorine molecule. It's diatomic. It's diatomic because they're more stable being together. So when you look at that chlorine or that iodine, what you're saying is that that bond energy is one of two things. It's either how much energy you have to put in to break a bond, and that's kilojoules per mole, 150, 240, whatever that number is. And then you're going to look at how much energy, or that's how much energy is released when you form the bonds. So it's either how much energy you put in on one side of the pendulum, or it's how much energy is released on the other side of the pendulum. Okay? That's it. Now, if you look at these numbers, so let's just make sure everybody's cool, because if you start off wrong on this, it's going to be bad. It says how many bonds are broken in each molecule of iodine, and what is energy involved per 1 mole? So here's what's important, is that that's how much energy there is if you make a mole of iodine, okay? Don't get weird, it's just 150. So that question number 2 is the energy involved is just 150, okay? Don't make this weird, it's the simplest question you're going to get. Now, where it gets a little bit more tricky is when you get to question number 3. It says, how many bonds are broken in each molecule of chlorine, and what is the energy involved in breaking the bonds into 3 moles of chlorine? So, if you look at that equation, where you have I2 plus 3Cl2 yielding 2 equal 3, okay? So, you've got 3 moles of these items, not 3 molecules, okay? This is energy per mole. So if you look at this, you've got 3 moles of this. Each mole on your chlorine costs you 240 joules. So that means if you have 3 moles of it, you multiply that by 3, it's not a big deal. So that answer on number 3 is around 700, okay? Because you're breaking 3 moles of these bonds, okay? Makes sense. Now, when you get to question number 5, how many Nickel bonds are formed in the making of a single molecule of iodine trichloride? So with that one, here's what you've got. 1, 2, 3, okay? So this is what, in a schematic, what this thing is going to look like. You have 1 iodine surrounded by 3 chlorines. This is what this would look like, okay? So each one of these is a bond, and each bond is going to involve 210 kilojoules of energy per mole. So with that one, you need to take into account, number 1, the fact that you're forming 3 bonds. Each one is 210, okay? So keep that in as just a simple multiplication. So what you need to look at is here's the big picture. It's question number 8. So if you've done everything right on question number 8, it says more energy put in to break the bonds and more energy released in the formation of the bonds. You should see that there is more energy released in the formation of the bonds than there is energy input to break the bonds. Okay, that was the whole point of me laying this out. Okay, we're going to look at energy broken, then we're going to look at energy formed. Okay? So on number 9, the overall difference should be around 400. Okay? Should be around 400. So what that means is if you do this reaction, what you would see is if you did this like underwater, in air, or whatever it is, you're going to see the surroundings warm up because this is releasing more energy than what you're putting into it. Cool with that? Okay. Now, let's talk about that second set of questions. So, you're going to make and you got a delta H of positive. Okay? So, start with this. Bethany, is this an endothermic or exothermic reaction? What'd you say? How do you know? You're right, but how do you know? That is positive delta H. So right away, you should be able to look at that without hesitation. Oh, positive delta H, endothermic, because you remember that for today, because we need to know that without fail for today's lesson. So when you look on, like for example, on number 4, how many grams of nitrogen gas must react to produce an enthalpy change of 1 kilojoule? So you're going to start with 1 kilojoule, okay? This is just stoic. What do you have to get rid of? Kilojoules. Okay? So we need some relation that involves moles. Oh, look. We got 163.2. Now, so the 163 is going to go down here. But this is what you have to be careful of. This is a stoichiometric relationship. So this is how much energy there is per 2 moles of N2O, O2, N2. It isn't just, so it's just a stoich, just like you're used to doing. It's just a mole ratio. So down here, you want to know how many grams of nitrogen. So up here, you need to put 2 moles of nitrogen. Now, if they just ask for moles of nitrogen, you could stop right there. You're done. But it asks for,
Grams.
so 1 mole of N2 is 28 grams. So that answer, for example, to number 4 should be between 0 and 0.5. Your answer to number 3 should be in kilojoules, should be around your age. And your answer to number 5 should be high 20s.
Okay.
We're good?
Good.
Yes.
Going once, going twice. So, stop you on the camera.
Sold to who?